compared in the industry, compared in relation to the resulting properties, to the resulting or to the process parameters, to the prepreg, so the material you can use, and of course more on commercial of the production costs you have. So depends on cycle time, on dimension of the parts you can produce with compression molding or with injection molding and so on. So first, on next slide, I want to show you that it's not the latest here. It's not the newest one. Unfortunately, you find not so much statistical report, but the trend is clear. In compare of production of thermoplastic fiber reinforced plastics in Europe, of course, not across the world, but you see compression molding, and it's something not in consideration of typical short fiber injection molding. This is not here because this is something typical plastic process with some better properties of the part. So this is especially summarizing of long and endless fiber reinforced plastic parts made by compression molding or injection molding. And what you can see is that we have a nearly stable amount of compression molding applications, and a huge increase in fiber reinforced plastics with injection molding technique. So, well, one big issue when you are looking on injection molding process is the fiber length reduction. So, looking here on it, I think it's clear. In a typical injection molding, you have some pellets. This are still chopped pellets with fibers inside. You start here with a typical long fiber pellet you use with a fiber length of 10 millimeters, and then you go in the plastification process. You have a high shear stress in the twin screw extruder due to the mixing process and the measuring process, the melting process of the granula. And along here, for good mixing, you also get a reduction of the fiber length, because the fibers are, due to the shear stress, have fiber breakage, they get broken. And so you have always, you never can, when you use this technique, you cannot avoid this. You always have a fiber length reduction in the plastification unit, and then also when you have the injection process into the mold with higher velocity, you also have a fiber length reduction in the mold. So at the end, when you have the part, start with long fiber granulat or long fiber pellet, you have a fiber length of average fiber length, let's say something between 1 and 2 millimeters. If you really have a smooth process, looking on your low shear rates and so on, slowly in injection molding, you have not so thin walled parts, you can maybe reach 3 to 4, 5 millimeters on average. Some pipes are longer, some shorter, but longer it's not possible. Okay? So this is the big disadvantage of injection molding when you use it for fiber reinforcement. But you have to look on the properties resulting, because fiber length is not the one. You only also have, due to the process, a fiber orientation. Yeah, in the process, you cannot align the fibers as you want it for the load. You can a little bit play with a runner system for the part. You can a little bit play with making some more runners on specific local positions on the part, but you always have a fiber orientation in the injection molding process with so-called 3 layer. Normally have top layers with the fiber orientation in flow, and perpendicular, and fiber orientation in the middle, perpendicular to the flow. So the thickness of the layer depends on the injection velocity and of the viscosity of the material and so on, but you always have this orientation in the part. So the fiber length reduction is someone, and the fiber orientation you cannot so much influence. Okay? So now when we look on the properties resulting in injection molding, we see injection molding we cannot use endless fibers, we have fiber reduction and we have more or less random fiber orientation. Well, is this so terrible in compared to compression molding? Well, we can say, especially tensile modulus, if the fiber lengths have around about 1 millimeter, has reached already a really good level. So with longer fibers, you cannot influence the tensile modulus so much more. Okay, you can influence, but then you need really endless fibers perfectly clamped. Then you can reach a higher amount of tensile modulus. Also, with the tensile strength, reach already in the area of up to 10 millimeters. It's for glass fibers here. Always already a good level. The main dependence of longer fiber is the impact strength. So with the longer fibers, you especially can increase the impact strength. Yeah? So when we look here in automotive application, as you can imagine, impact is something really interesting for automotive applications. So if you have a crash, especially in the front end or in back, it's interesting to get high impact strength. So there, endless fibers would make especially sense. Tensile modulus is not so, you cannot reach so much anymore. Also tensile strength, but especially tensile impact strength. Okay. So this is something then was thinking to get longer fibers, was in development from Kraus Maffei. It's now injection molding compounder 10 years ago, maybe. Yeah. The combination of these technologies, because it's something to get longer fibers in the part, but also to reduce the energy you need to produce the part, because when you know getting a compound of matrix and fibers, you have first a compounding process to mix the fibers or get typical fiber content and to edit your specific additives you need for some stabilization and so on. And then you cool it down, make the pellets, and then you get another heating process in the injection molding. So you heat it up again, and then you make your part. And this is injection molding compounder. You can combine it. You have a compounding process, and then go directly in the injection molding process. So you have a lot of advantage, because you are totally flexible what you use for your compounding process. You can go inside with fibers, typical content you want to have. You have here a twin screw extruder for making your compound, and then you have such a melt buffer, because compounding process is always a continuous working process. Injection molding is discontinuous, because you have plastification, injection, and then you have the packing phase, cooling, and this time you have you have a stop in feeding the injection with the material. So here you can reach longer fibers, so you can go a little bit higher, especially in the properties compared to a classical injection molding process. So here you see for injection molding compounder, but for glass fibers, a typical fiber length distribution over the frequency. So how often it is. You see, with the classical long fiber injection molding process, you have fibers, especially in the area of 0.5 till 1 millimeters, and then you have really a sharp distribution of fiber length. And with the injection molding compounder, you can reach a higher amount of longer fibers. Okay. So you see here the average fiber length. When you look, use really long fiber, you have average of around about 1 millimeters, and with injection molding compounder, you can reach something about 4 millimeters. Okay? So, now, when we want to have longer fibers, injection molding compounder, we can read something a little bit higher, but we cannot use endless fibers. Now, looking on conventional thermoset, you have fibers, then you make a textile process. For example, you have a woven weaving process or multi-axial laying process, or you have some warp knitting or knitting process. You get a textile pre-preg, then you go with a matrix inside. This you have in the liquid composite molding, like racing transfer molding, some finishing, and you have an end product. This is a typical line for a thermoset. But when you look on thermoplastic, it's much more complicated, and you have much more possibilities to deal with the matrix, with the fiber, and with the process. So, two big differences. You have in direct manufacturing, you come with the fibers and the matrix, have an impregnation and consolidation in the end product. This is something typical extrusion technology or compounding technology. Yeah? The matrix and fiber goes close together. In the plastification, you have an impregnation of the fibers, means surrounding each fiber with a matrix. Consolidation means cooling down and product. That's it. But if you want to have longer fibers, you need some textile pre-preg which you can use. You cannot feed a woven fabric in injection molding plastification units. It could be a little bit difficult. So you have so-called indirect manufacturing. You have the fibers, a fiber process, textile process, for example, and you have some impregnation with the matrix direct in the textile, and then you have so-called pre-preg, a thermoplastic pre-impregnated material. You use it for the next step for forming and consolidation, for example, for thermoforming. So this can be separated. It must not be the same OEM. So, for example, someone buys this pre-preg and uses it for its techniques. Yeah? It can be separated. And now it's only imagine how production path you can go, and you have a lot of variations you can use to go on a pre-preg. And it's the end of the final part for thermoplastic processes. So, for example, the fiber can be really single fibers can be a yarn. You can go directly in the textile process for weaving, or you can directly go in the impregnation with the fibers with the matrix. You can come with fibers in the textile process, then additional textile process of fibers, textile and matrix in the textile geometry, and then in the impregnation. And so we have a wide variety of process and combinations of this you can use for thermoplastic. And some specific I want to have a short look on. So, always problem with impregnation. It means when we go back here, we have a problem with the viscosity of thermoplastic melts. In compared to thermoset resins, the viscosity is 100 to 1,000 times higher in compared to thermoset resins. And that's the reason why it makes it so complicated to make thermoplastic parts with thermoplastic prepregs. You can see here viscosity of typically polypropylene, polyamide, where something in the viscosity, in processing viscosity, something between 100 to 1,000 Pascal seconds. In compared to epoxy resin, we are below 1 Pascal, so it's something around about 100 millipascal seconds to 500 millipascal seconds. So viscosity means the flowability of the thermoplastic melt. It's much more higher, and you need much more pressure and much more time to get to melt flow into a textile prepreg. You see here, the problems we have with the impregnation is to get the thermoplastic melt in the textile prepreg. So the fiber bundle, and this we also know at natural fibers, has a lot of single fibers, and they are then produced to textile prepreg. And we have some flow gaps. Here you can go into textile, but especially difficult is to go into flow gaps between the single fibers, because they are often really compressioned that you have not so much flow gaps between it. And that is the problem to get thermoplastic prepregs. Okay, so to make this impregnation, you have normally 4 four path or process paths you can use, but especially common is to get a direct melt impregnation, powder or fiber impregnation, so-called film stacking. We will go later on. And now looking on the premix you can make with natural fibers, especially is something woven hybrid. So you have a woven fabric made from natural fibers with some matrix fibers, for example, polypropylene or polyamide, thermoplastic. You can use. Also, you have hybrid yarn, so it's like a commingling process. You have polypropylene fibers, some natural fibers you can so-called commingle. So you always want to have the matrix close to the fiber, so you can reduce the flow lengths during consolidation. And these are typical pre-break materials you can use. Okay, so to make the pre-breaks, you use textile processes, which you can also use for classical textiles. So in former times, in the development of technical textiles, you look on classical woven or non-crimp fabrics, and then you try to get it also for application for natural fiber composites. So you can use these classical processes also for natural fibers and for fiber reinforcement, but the problem is in the small process parameters and small things. We have to look on the geometry of the feeding system, of the needle system, and so on to get this pre-breaks. This is much inside knowledge of the textile producers and producers of textile machines for technical reinforcement. So, looking on non-woven, you have, for example, chopped fibers from a yarn which is colored, or directly fibers coming from natural fiber producer, and you go in normally you have a mechanical binding with such needle beams, and the properties of non-woven pre-breaks is that they have more or less easy impregnation and a good traceability because the fibers are not so long. But of course, the disadvantage is that you have especially a random fiber orientation. So something when you use is a non-woven, for example, a glass mat thermoplastic pre-breaks, you have a random fiber orientation, but you're relatively good for impregnation, have a good drape, and they are not so cheap. Not so expensive. They are much more cheaper. So woven fabric, these are typical structure of the woven process. Typically it's plain, weaving, and the crimp goes down. Crimp means the curving of the fibers goes down as lower is the bending stiffness, but as low as the bending stiffness, as better is the traceability and the flow. So you can much more have a better traceability for complex shaped parts, for example. So a lower crimp means, of course, good traceability and higher stiffness and strength of the laminate, because the fibers are straight, more aligned as here. Because here you have a reinforcement also in Z direction, not only in plane direction. So this is typical. Some RAM pictures of carbon glass fibers, and here you see natural fiber, some woven fabrics. You see some binding technologies. So advantage, of course, is the high fiber volume content you can reach, and of course the high variability of area density, because it depends on your structure of your woven fabric. The disadvantage, I think that's clear, is especially the fiber orientation is fixed on 0 degree and 90 degree. And you can only in the stacking sequence you can make other fiber orientation, but in one you have only fiber orientation 0 and 90 degrees. So, but for us it's much more interesting also for non-crimp fabrics, because you are really flexible in fiber orientation. You lay first the fibers in some processes, and you have then some fixation by a knitting yarn, and this knitting yarn, or also the knitting yarn can be a matrix system, can be, for example, a polypropylene yarn, and the fiber orientation you can decide normally much more fiber orientation, but typical is 0 degree, 90, 45, 30, 50 degrees, plus minus. And well, here really advantage is flexible fiber orientation. Also, it's a very good traceability because it's only fixed with this knitting yarn, and you have also a high variability of the density. Well, the disadvantage is to use lower yarn counts. You cannot take yarn counts with more than, I would say, 1,200 ticks for glass fiber, so this is really limiting in the fiber yarn count. And well, the good traceability means a lower stability. You have to be a little bit careful in handling of non-print fabrics. So, textile preprint summarized. What is especially interesting now are for us non-print fabrics with some optimization of properties you have. You can reach and in production costs, and especially in the application for parts for thermoplastic-based resins. So, one typical melt impregnation technique which is used is a thermoplastic melt, which you have a slot die and goes directly onto textile fabric with a thermoplastic melt. You have some often a double belt press. You have a consolidation to get the thermoplastic melt inside of the prepreg, and then you have it roll to roll. As Professor already mentioned, it's really efficient. You have roll to roll process for the prepregging process, and normally you use typical thermoplastic melts, thermoplastic types, polypropylene, polycarbonate, polyamide, but also other technical materials. Another way is to impregnate not the whole textile prepreg, but make such so-called fiber impregnated thermoplastics to take the yarn and to try to get the matrix already in the yarn in the form of a powder or a thermoplastic cover. Okay? So then you have a hybrid yarn already, and then you can go in textile process. You have not to impregnate the whole textile, but you do this already before in the yarn process. So also typically is then so-called commingling. We have the single fibers of the reinforcement fiber and polymer fibers, single fibers, and you have such an air nozzle and mix the fibers, so-called commingling. And then you have a hybrid yarn which consists already of the matrix and the yarn, and can then go in some textile process. Non-cream fabrics can make from, but also woven fabrics is really popular. So in something, we have then some really detailed processes for making thermoplastic prefix with natural fiber composites, with natural fibers. This is so-called film stacking. We have again textile prepreg and have some thermoplastic film, and goes also in a double belt press for consolidation with a heat and compression, and try to impregnate the textile prepreg with a thermoplastic film. So then you have your prepreg, and now it's quite interesting what you can do then, because now you have a prepreg with endless fibers, and some typical is so-called direct processing of long fiber reinforced thermoplastics. You have, for example, your thermoplastic prepreg. We are coming from a film stacking process, for example. You go in a preheating process to make the thermoplastic matrix melted again, and go in the compression molding process. So we have some endless fibers here, but additionally you can add it with some compound of a classical compounding process, extrusion process. You have some compound here, and you can combine it together in a press, have a compression process, and you get some fiber reinforced part with chopped fibers, so fiber lengths of 5 millimeters up to 10 millimeters, but a additional local reinforcement with endless fibers. So you can adapt the endless fibers on the forces you have on your part. Okay, you have an average fiber reinforcement in the whole part with a random fiber orientation and a local fiber reinforcement with endless fibers. So this is something, for example, from company Lanxess, made some parts where they applied this process for some sandwich compression molding. We have some parts already this compounding process, and you add some thermoplastic pre-breaks to make some sandwich structures. Okay, you have an endless fiber reinforcement at the top and below, and between you have some short fiber reinforcement. So looking on the properties you can reach and compare compression molding with long fiber thermoplastic and injection molding long fiber thermoplastic. What we can see, summarizing in red, so compression molding is better because of longer fibers you can reach. In the mechanical properties, injection molding is some better in the effectivity of the process in the coast because of the shorter process. You can make much more efficient parts with it in the cycle times. You can additionally integrate some functions and so on. So now something I'm switching on technology developed from Klaus Maffei, so-called fiberform process. So I'm not sure if it comes in your. Also, yes. So I can switch. This is something we use for some structural parts. I think Caroline then Amit will introduce and present for natural fiber composite. So I will switch. And it's a machine which we could use at a Klaus Maffei company in Munich for makes this testing parts. And something what we are using is to make also sandwich panels where we have top layers with textile fiber reinforcement, and between the layers you can inject your melt, so you get local reinforcement, sandwich structures for high bending stiffness, and you need, as you know from bending, it's especially something you need high tensile modulus at the top layers. You can use also the typical application for producing parts in the injection molding process. And here you have to get some property feeling. If you have the poor matrix system without reinforcement, you reach a flexible modulus with the polypropylene around about 1,700 megapascal. If you have a short fiber reinforcement in normal injection molding, you reach already around about 5,000 megapascal. So you get a doubling up to reinforcement is 3 times higher than the poor material, but with the local reinforcement, you see here you get additional increase, especially twice. Yeah. So it's the local reinforcement. You have to look which forces you have in your part. It's the local reinforcement here made for sandwich structures, for bending stiffness. You can erode huge, really good mechanical properties. Okay, you see it here in a polished micrograph. You see the fibers, the fiber orientation 0 and 90 degrees on the top layers. In between we inject the melt. So this is something you can locally reinforce in injection molded part with textile reinforcement. Not only short fiber reinforcement, but to integrate textile reinforcement into the mold to make parts with endless fibers in the injection molding process. Okay, and here you see this is something from a show 2008, well it's already sometimes years ago, which application in the car you have already for this part. To make in compression molding with endless fiber reinforcement, long fiber reinforced thermoplastics, direct processing in compression molding process, and we have a lot of parts, especially in the front for crash here, but also underfloor construction. It's an engine undershield here, also in the underhood shield at the back, and so on. Okay. Last but not least, something not for reinforcement, but you also can release natural products, especially veneers would be some topics then to go in thermoplastic parts to make decorative things. So, for example, one typical is so-called insert molding or in-mold labeling. You know, maybe is something you have some decorating material. You can print it. It's pet printing, for example. Has some thermoforming already in the mold or outside. Then you have some punching to get the dimensions, and then you can back inject such parts. Okay, you integrate it in the mold, and you make some back injection, and then you have your demolding. So these inserts can be some natural materials, for example, really popular wood insert, veneer insert, and this will be something as an auto application of the Wagenführer will say something, and Caroline? Yeah. Yeah. Okay. So this is the same with in-mold decoration with vacuum assistant, so you can fix the material at the mold cavity wall. Okay. Last I prepared some maybe a known new cell process is something you have an integration of a gas, a supercritical phase into the polymer melt in an injection molding process, and what you can reach is to make the gas mixing with a melt. Supercritical means it's totally solved and in the diffusion process in the melt under high pressure, and then you go in the mold, you get a rapid pressure decrease, and you get the so-called nucleation, and the cell grows, the gas releases out, and you get an cellular injected material, and so you can decrease the light weight. It's originally made not only for lightweight construction, but it's now also used to get much more lighter materials in the injection molding process. So this is something you can also combine with some reinforcement, and this is something really special you are dealing with. Okay, so that's all.
Thank you very much, Dr. Trosch, for a very insightful and very informative presentation, even though he has a very long night, last night. Very impressive. Dr. Trosch also he's a very key person who helped organizing this seminar. Without him, this is not possible. Okay, could you give him a big round of applause? Is there any question from the audience for Dr. Trosch? มีคำถามจะถามไหมคะถ้าไม่มีก็เดี๋ยวถามตอนกลางวันก็ได้ maybe at lunchtime you can approach him and ask him some question. Yeah. But I would like to move to the next speaker for this morning. It's Mr. Stefan Krapper. Yeah, he has been with Cross Maffei for 5 years. He's an expert in injection molding. He's going to make presentation on behalf of Mr. George Hosinger, who's a Vice President of Cross Maffei. Okay, so if you're ready, please join me in welcome Mr. Krapper.
Give me a minute to change the adapter. thank you, Dr. Arisawa, for the kind introduction. So everybody can hear me? Okay. So let me introduce myself again. So I'm an injection molder from Composite company. I'm working for 5 years at Composite, and I would like to present you my speech, New Potentials of Lightweight Structures for Extrusion and Thermoset Products and Applications of Reinforcements from Short to Endless Fibers. Here's the agenda. I would like to start with a short introduction. Then I would like to focus on the resin transfer molding technology. It's usually it's on the thermosets, but it also is about thermoplastic RTM. Then I would like to show you the fiber foam approach. It was already mentioned before. Later I would like to go on some wood plastic composite related technologies, and then we'll close with a brief summary. So the importance of lightweight design is it's obvious. Yeah? So CO2 emissions are directly linked to the weight of the vehicle. Professor Kroll mentioned in his speech earlier. So now if you reduce the weight of the vehicle, we can also reduce the fuel consumption. Additional, again, by reduction of the weight, leads also to secondary effects like downsizing of the engine, of the drivetrain, even to other components like brakes or suspensions. And as we learned earlier in the morning before, we can increase the range of battery electrified vehicles. So on the upper left side, you can see the spiral. So cars and vehicles, they became heavier and heavier during the last decade. So the body was adjusted, so we have more heavy chassis, so we have high performance engines and also a large tank, or everything for more convenience, for safety, and for better quality of the cars. But as you can see on the other hand, more weight leads to more fuel consumption. So now plastics are helping to reduce weight without compromising the safety and comfort features mainly responsible for the upward weight spiral. So let me give you an example. The Volkswagen Golf, it weighed 800 kilograms when it launched in 1974, and now it weighs 1.2 tons. So thus material producers, car manufacturers, suppliers, processors, and various institutes like universities and other associations have taken up this challenge of reducing automotive vehicle weight. For example, car production, for car production already many parts has been substituted by plastic parts, fuel tanks, suction pipes, bumpers, gear bearings, dashboards, headlights, and also the glazing, the windows you can see on the left side. And you can reduce the weight, and it will result in lower fuel consumption. For example, 100 kilogram of weight reduction brings down the fuel consumption to 0.35 liters on 100 kilometers. So there are several parts. The glazing, the side, the interior of the door, the dashboard, and also lights. Almost everything is made in polymers now. But cost-efficient plastic manufacturing solutions can help to consolidate parts and reduce the number and scope of processing steps. This is the issue number one. So, and the second is while reducing weight of the finished component or the system. This is the second issue. So you gain other advantages, not only by reducing the weight, but also by reducing maybe processing steps. So And now I think this is one of the main goals, the replacement of metal material by engineering thermoplastics and also fiber reinforced composites and hybrid composites in the automotive core structure, body or powertrain offers significant weight reduction potential. So the greatest reductions can be achieved in structural components. And for example, underbody covers, dashboard, roof, front end, or door modules. And now fibers get important. Yeah. So this is the main goal, to reduce weight, and we can achieve it by using fibers. So it's a market demand we have here, which forces us to innovate new solutions. So it's not only the lightweight construction, it's also hybrid concepts, and very important, the integration of complementary functions. And also carbon footprint has to be reduced, and now we have the cost pressure from the market. So this is a very important slide. So on the left hand you have, so it's a schematic sheet for technologies we are using. So on the left hand you have reaction process machinery. So these are the thermosets. On the right hand we have the injection molding technologies. And let me start from the right. So it's, for example, it's non-reinforced injection molding, and now we can enforce it with short fibers. So this is we have two arrows. The one increasing cost efficiency, and the other one increasing structural strength. So, and for the injection molding technology, because we have a very high-scale production, it's very affordable to produce. And if we combine technologies, this is injection molding technology still, but it's combined with extrusion technology. This is the IMC, the injection molding compounder for long fibers we saw earlier. And now you go from short fibers to long fibers to endless fibers, and now the fibers get even longer, long fiber injection, and also high pressure resin transfer molding. So it's the longest fibers, and of course the high strength. But you want to go into this direction. So you want to be cost efficient, and so some of our experts say all technologies will go in this direction. So maybe in 5 or 10 years we won't have any longer fiber set technology or thermoset technology. So this is something we are working on very hard. So material combinations allow for a variety of tailor-made solutions. I think this is one of the key issues. So by using different thermoplastic matrix materials, for example polypropylene or thermoplastic polyurethane, and embedding various fibers now, glass fibers, carbon fibers, and so on. So along with the use of additives, material properties can be custom tailored to suit specific requirements. And I think this is very important for all future technologies. So this is a picture for, this is a slide which is picturing the injection molding compounder. It was shown before, and yeah, now I think it's also important for treating fibers. Yes, especially natural fibers. You have to treat them very gentle, and you can do this, of course, using a twin skew. Using the twin skew, it's combined with the piston injection of the injection molding compounder. But this is a very sophisticated technology, and of course, we also want to facilitate fibers also with standard machines, not only with compounders. But I will refer later on this technology. Let me show you, and let me give you a focus on resin transfer molding on the thermosets. So the process, I think it is known to you. So you have the material, so the tape. It will be cut out and stacked, and then it may be formed and put into the mold. It is evacuated, and then the polyol and the isocyanate is mixed up and injected into the mold, and under high temperature and high pressure. And then you take out the part. So, for example, due to low viscosity, polyurethane resin penetrates and impregnates the fiber reinforcement easily and with less fiber displacement, and thus this enables short injection times and shorter overall cycle times. So also this technology gets more and more advanced. So this is what you need to perform the process. So you need the preform center where you prepare the preforms. You need RTM automation. You need, of course, a press cell here on the upper right, and shuttle tables for quick tool changes. Then you have the metering machinery, so it mixes the isocyanate and the polyols and inject into the tool or the mold. And of course, you need some milling cell for finishing or for afterwards treatment. So we already have a very broad spectrum of RTM technologies already. So, for example, high pressure RTM. So you have wet pressing, you have thermoplastic RTM. This becomes more and more demanded by market. Everybody is asking for thermoplastic resin transfer molding. Then we have compression transfer molding, and we have surface with resin transfer molding. I will refer later on some of the technologies. So these are typical RTM applications. You use them for automotive, agricultural, for transportation, for cars, for the huge structured parts, and even for sport industry, for boats. And this technology, and companies have experience with the technology for more than 20 or even 30 years. So let me show you some of typical applications for RTM and structural parts, especially used for carbon fibers. So you have underbody structures, you have seat structures, for example, side frame and the roof. So these are just some examples I would like to give for serious applications. So we have this carbon side panel for the Audi R8. So this is also a serious application. The roof is from the BMW M3, and this is all serious production. But you need a lot of manpower, and also it costs you a lot of cycle time. So it's cannot really be used for serious production with high scales. And now, also another example from Lamborghini, also I think it was a monocoque, the structural underbody frame and even parts of the roof were produced by a high pressure resin transfer molding. And I think this is also one of the most famous examples, because Maffei developed together with BMW the technology. It's also high pressure resin transfer molding for the i3 and the i8. You can see these cars now all over Munich. And this is, I think, one of the most famous examples only. But it's all, you have to scale up the production. So you know about the cycle times. So what can you do? You have to buy a lot of machines. But in the end, is that what you do not want? You want to have one machine with short cycle time. So this is also an issue. So you have sink marks due to different shrinkage of the reinforcement and of the matrix also. So in general, you cannot use conventional spray painting on the surfaces. So now this is about surface resin transfer molding. And if you have sink marks and other surface defects, like also welding lines, sink marks, pore pinholes or streaks, you need a coating. And now you can combine also technologies and use, for example, Kausmafai color form in-mode coating technology. So we presented this technology at the K trade fair in 2013. I think this is the part we showed. It's the roof element of the Roadster R1, and there are some details of the part itself. Substrate thickness about 2 millimeters, surface layer thickness 0.2 millimeter, fiber content about 50%, and fiber layout quasi-isotrope. So in cycle time 6 minutes. So now it depends a little bit if 6 minutes cycle time is sufficient for you and your production. So these are some of the main benefits. So it was a really world new two-step RTM infusion and overmolding process. So you can see the roof of the Roadster. And it was a high-quality paintable surface for carbon fiber reinforced polymers for automotive exterior parts. And yeah, it was a joint project among technological leaders of polyurethane and lightweight manufacturing companies. So it's not always Kausmafai. It is always many partners are involved. I will show you later. It is a combination of high performance lightweight parts with high quality surface enhancement. And these are two megatrends. So one thing is if it's a lightweight design, but on the other hand, you need a really nice surface. Otherwise, no customer will use it for its products. Even cars, you know, you need meet very high specifications. So these are only some references from customers for this specific RTM technology. And now there are some of the development partners, because you need a strong network of partners, also universities and other partners for the different tasks. So let me show you the fiber form approach. Now we are, if you can remember the slide with the two arrows, we are heading to the right direction. And fiber form means much more faster cycle times. Still, we try to improve, but I think this is yeah, one of the main future directions. So let's have a look at this chart. It is we have injection molding on the one hand, and we have compression molding on the other hand. In the previous speech, we heard a lot about injection molding and compression molding. And with injection molding, you have high choices of complexity of your parts. And compression molding, you have the advantage on the fiber lengths and the material properties. So you can see what makes sense, you combine both technologies. So this is what Kausmafai did. So on the one hand, injection molding technology, and on the other hand, thermoforming technology. So you can achieve very high stiffness, strength, and also energy absorption capacity. And you can achieve high component complexity. So this is a combination of the two technologies with high strength and stiffness, very high freedom of design, high level of functional integration. And I think this is a very important point, because you do not need only to make the part lighter itself. You need to integrate functions, so you can skip several assembly steps, for example. And also you already have a high degree of automation and short cycle times. So let me show you where everything started. It started with a two-stage process. And the more stages you have, the more complicated everything gets. And You have, for example, an organic sheet. You will heat it up in an oven. So now you can make a preform. Then you will cut the preform. You will now put it into the injection molding machine, and you will overmold it, and then you have the finished part, and then you can stack it. But we tried to reduce the steps, because this is the current situation. This is one example from Audi, and the costs for carbon fiber reinforced parts right now are too high for use in real serial production. And I think BMW, so they are very advanced by producing a whole chassis at the i3 or the i8, but for all other cars, production costs are too high. So we have this vision of reducing the costs for material, process, lacquer, and we need to bring down the costs to get these technologies serious. So now, by reducing the steps, so you can achieve this. And now we have a one-stage process. So again, you have the organic sheet. You will heat it up. You will preform it inside the mold. Okay, mold now needs to get more complex, and I think a lot of industrial know-how is in this forming inside the mold, but you can directly aftermold it, and you will have the finished part, and you will skip several steps. So this is the finished part, and it's some test part to substitute metal. Let me show you some other examples. For example, this airbag casing. It was invented also several time ago together with Takata. It's a processor, and with bond laminates for the materials. Siebenwurst, they are the mold maker, Lanxess, also material manufacturer, and Composite company. And you can achieve almost 30% of weight reduction compared to steel or aluminium. This is another serious part. It is made by Audi, and if you buy, I think it's the Audi A6, and you order the sound system. It's I think it's a Bose sound system. It is you can find it in the back of the car, and it was invented also together with Composite. And I will show you a nice video how this part is made. It has two organic sheets. Maybe you can see it not very clearly, but you'll see it later. And you have the reinforcements on the back. They are all injection molded. And so the most interesting thing is that the part it is not cheaper. It's even more expensive in production costs, but it reduces a lot of other costs, for example, assembly, because of the function integration. Okay. Also included nice music. This is a production cell, and we have a complete automation. We will see it later from another perspective. So the gripper takes the organic sheet, put it into an infrared oven. It's above, on top of the machine here. The part is heated, and again, the gripper takes the organic sheet, puts it into the oven. This is now from above here. Quite simple construction. It's an infrared oven, and the mold is closing, and the organic sheet is put So let me give you some other examples. So again, okay, here's the organic sheets. We have the polymer, and it's a complete finished part. Again, another example, and you will, I think some other colleagues will refer later on this test beam we showed at the KE 2013 trade show. It's a hollow profile, and I think I also prepared a video which quite explains a lot for itself if it starts. No, it's not the videos. It's a hollow profile, and we have a local reinforcement. So this is a little bit special, and we also have some function integration, and this is a part. And I think so the video pretty much explains itself. Again, the music. But now we do have more description. So this is called the fiber form test beam. And it's inset molding and joining of consolidated composite laminates in a one-step process. We have two cavities in the mold, one main and one auxiliary cavity. And you have skin better from the other side. Automation is working. So these are the organic sheets. This is the local reinforcement. It's heated up in convection overlay. It's got a lot of execution, and it's much more better for images heat. You also have infrared temperature monitoring, and also some infrared heater field to reheat the surface. So the local reinforcement is really also it's placed on the preheat laminate. And we have a special heat equipment for very recycled things. And the second is also advantage. Thermoforming process started, and then afterwards directly get injected. So we have two cavities, and afterwards the part is assembled. So now we do have the finished part, and it's ready for assembly. This is for feeding, and you can use different types. But usually it's no rocket science. So I want to tell you you can handle it. Of course, it's a lot of automation. Any personnel or any staff, but you can handle this technology. It's not too complicated. So one last example, and now it becomes interesting. It's so this is for ski binding, and I do not know. Maybe you're not do ski so much in Thailand, but we do in the Alps, and this is for touring skiing, and you have to carry your ski by yourself. And I think it's all for the sports equipment. You know, if you buy sports equipment, you do not really care for the money, because you want to perform well, and if you have a nice tennis racket, you will buy it, even if it's €100 more. And this is the same for very sophisticated sports technology, and you love to have very light ski if you have to carry it up the slope. And now this goes into a high-scale production. So this is ski binding completely, and it's only one part of it, but it is quite, it's not very easy to produce, and you have this composite or organic sheet, and you will shape it by thermoforming, and you have some edges. They are only 1 millimeter thick, and you have a hot runner and a needle gate, and you need very precise placement of the organic sheet for the molding. Otherwise, you will have a fail part. And I think the scale is more than 100,000 parts a year, and this is outstanding for these technologies. So if you talk about producing some rooftop for some cars of limited editions, or even BMW i3, you only need some machines, but now it's a really high-scale production with really short cycle times. I just wanted to show you that we are already able to produce for serious application, not only for research. So now some wood plastic composite related technologies, you can make two approaches. So the first one is using a standard machine. So you use the natural fiber material, for example PVC and natural fiber, or polyolefin and natural fiber, some additives and master batch, and you can produce with a standard machine several application of products. And the second approach is the injection molding compounder. We already heard today a lot about this technology, and now you can use direct compounding, and you can use your own recipes now for the fibers, also for the materials, the resin, master batches, additives. You can almost put everything into a compounder, and you are able to create your own recipe of the resin and of the material. So, of course, if you would like to treat natural fibers, you have to use some specialized, for example, screws on the right side, and they are deep cut screws, and for reduced dissipative melting. So you will have an increased heat conduction by the heating elements outside of the barrel, and rather no shear heating, because it will maybe destroy the fibers. And also you can use a specialized non-return valve with an enlarged stroke or enlarged flow channels, so you do not destroy fibers inside. Also for the injection molding compounder, we have several, so these are some multiple tools and multi-combing elements that are arranged to one combing zone for natural fiber processing. So there are already there's already several expertise in processing natural fibers. So this was also one slide concerning processing sisal fibers. So during sisal fiber yarn production, the single fibers are wetted with oil to get them processed, and now these yarns are easily to process on the IMC. Because of the oil, there's no sticking on the polypropylene matrix. So maybe the fiber experts will have more details on this. And so coupling agent cannot improve it, and therefore these yarns, for example, reach only very low mechanical properties. And so we did several tries with chopped fibers, which weren't oiled, with Brazilian sisal, and we did also some tries with chopped fibers from Africa, and but still the fibers do not reach the properties of artificial or of industrial fibers we use today. This is one last example we did some research on combining the technologies again, and we have a natural fiber mat which was kind of preformed and was reinforced by this polypropylene ribs, and again it was coated, in-mold coated with color form technology to gain this good surface, and is only one example of some experience that Maffei have with treating natural fibers. Let me summarize. So I would like to focus again on thermoplastic materials. So we have very short cycle times, and we have a very fast and reproducible process without chemistry, of course, and we have a highly automated process. And we have various post-processing options you do not have with thermosets. For example, welding, surface decoration, and so on. And so you can you also have better storage stability, and also good abilities, so high impact strength, and this especially for the lower temperatures. But we are still, our material suppliers are improving. So this is all suitable for mass production. And yeah, let's have a technology assessment of this technology. And the production of very complex three-dimensional geometries is not possible. So it's this freedom of design which is a benefit, and components with near net-shaped contours do not need any post-processing, so you get flash-free parts, for example. So this is almost never the case in treating thermosets. So, and again, integration of additional functions, for example, antennas, sensors, inserts, metal inserts, in one and the same processing step. This is a very valuable asset. And you have now various process and technology configurations in combination with other injection molding technology or methods, as you can see, for example, coating, mold coating. Also, you can use foils, and I think this is also quite rather old technology, but if you do not have a really nice surface, you can use a plastic foil to conceal the surface defects. You can also use electrically conductive surfaces, or even surfaces with liquid or gas barriers, UV and weather resistant surfaces, scratch resistant layer, and you can also combine again a foamed surface for visual effects and haptics. It's again, it's some kind of color form technology, and now it's, if it's foamed, it's skin form technology. So this is again a combination. So this is some coating, and this is these are fibers, woven fibers, and you can combine them by using using combination of the technology. So you have a ready-to-use part recycle from a complete production cell on a standard injection molding machine, and this is also important for the staff, the personnel, the operator, we have to handle all these processes. If you have only very specialized machines, it becomes very difficult to get qualified personnel. Yes, and again, some other benefits by coating fibers. Of course, you can only achieve this with a really strong partner network, and I think this is also one advantage of Maffei company. We do have partners all over the world. So, of course, we are a machine maker, so you need somebody for component design, for the material selection, for topological optimization, for calculation, simulations, for the automation. So, because Maffei also has under one roof automation supplier, so it's included to our company. And we need someone for the production, for quality control, and for component testing. And everybody has to work together on this. And this is why you need a strong network, and you need the collaboration. Of course, also you need to collaborate with universities. Now, this is a statement. I think this hits the nail right now. It's so conventional polymers are still better understood than customized, reinforced polymer composites. So, yeah. So this is a quite young technology, and we are just at the beginning to learn and to advance this technology. And also markets may be not ready yet, but also markets has to be developed. And I think this is also again some issue of collaboration and working together on these topics. So I would like to close with this slide. It's again a summary you have with thermoplastic, injection molding, and combined with the treatment of long fibers. You have a reproducible and reliable process with low-cost manufacturing technology. This is important. You have reinforcements that are tailored to the load case, and you have a high level of functional integration, and you have a fully automated process. So you get ready-to-use components in very few process steps. So this experience we already have with treating fibers. So it started already before 2004, but this is one part which was quite important, and then some parts I showed you before, this door knot or this preformed crossbeam, this technology carrier you will recognize very easily because several research has been conducted on this, and the airbag container I showed you, and then from the trade fair the test beam. So you can already buy a fully automated production cell for production or for trials. So thank you for your attention. Let me know if you have any questions.
Any question for Mr. Krappa? No? Okay, thank you once again, Mr. Stephen Krappa, for very exciting new technology from Krasnodar, the world leading in injection molding manufacturer. Thank you very much. Next, I think we are going for lunch. It's lunch break now. We're going to come back again at around 1:30. Is this okay for you? The lunch is at the back of this room. It's just next room actually, next room. ค่ะก็ขอเชิญรับประทานอาหารได้นะคะเรากลับมาอีกทีบ่ายโมงครึ่งนะคะค่ะเจอกันค่ะ
Nobody can speak Dutch anymore. Oh, this is on the screen.
Ich glaube, wir sollen jetzt zum Mittag.
Thank you.
all biodegradable. Time it takes for it to originate.
มันอยู่ที่คนป้อนอยู่ที่คนป้อนอาจารย์สุทธิพรสุทธิพรดร.สุทธิพรเรียนของต้องขายไว้หลายเครื่องเลยขายไปลาดกระบังขายไประยองขายไปหลายที่แล้วหลายที่ก็อาจารย์ก็ให้ท็อปสี่ขายคือเวลาคนใช้แล้วมันถ้ามันไม่เต็มที่แล้วต้องปรับคือก็เอาหมากที่สุดแล้วตัดแค่เสร็จแล้วก็มันเป็นร้อย
ไม่ใช่แล้วโอเค
เพราะว่าโอเคมันเร็วกว่ามือแกะ
ไม่แล้วผลออกมาเป็นโครงเลยเป็นหมาก
ใช่แล้วถ้าเป็นหมากแกะ
แล้วยังมีแบบพวกเส้นใยไหมครับ
ไม่มันแยกมันกระท้อนเรียกว่ากระท้อน
ไม่เหมือนว่ามันต้นที่เป็นหมากเกลี้ยงเลยเกลี้ยงเลย
เป็นกะลามันเป็นเหมือนมะพร้าว
ครับ
มันไม่ใช่เที่ยงแต่ถ้าลูกไหนไม่แตกก็เอามาเดินใหม่แต่มันเร็วกว่าเครื่องที่ชาวบ้านหรืออะไรอย่างนี้
แล้วตอนนี้เล็งวัตถุดิบมาที่ไหนนะครับ
ไม่กระทบกระลาน
แต่ว่าส่วนใหญ่ปกติถ้าเกิดเป็นมันจะเป็นหมากเปียกใช่ไหม
ที่อย่างนี้มีสองอย่างมาสดที่เขียวเนี่ยเขามาผ่าแล้วก็ตะเาะแล้วก็ฝานแล้วก็ตากแห้งอันนั้นหมักสดเป็นหมักแกงเนี่ยต้องมีเครื่องกระเทาะอย่างนี้เหมือนใบพี่เนี่ย
แล้วเกิดของขายเส้นใหญ่เนี่ยก็จะเส้นใหญ่แยก
ก็ซื้อเส้นใหญ่มาต้องเยอะแล้วตลาดไม่รับ
ไม่เลย
ตลาดไม่เจอญี่ปุ่นไม่เขาก็คือ
เพราะอะไรครับเส้นใยมันคุณภาพมันคือเส้นใยไม่ได้
ชื่อมันมีงานวิจัยบอกว่าไอ้หมาเนี่ยทำให้เป็นมะเร็งมันก็เลยพูดกันไปแล้วคนมันได้ยินแรงยูเนส
ในเฉพาะฝั่งญี่ปุ่น
เฉพาะลูกค้าผมเพราะผมพยายามเช็คข้อมูลซื้อมาต้องเยอะเลยว่า
แล้วตอนนี้ซอสเนี่ยจะซื้อทางใต้
ซื้อระยองเขากระเทาะตัวเนี่ยแต่กระเทาะหมักแกงเสร็จแล้วก็ลงควันเพื่อกันแมลงแล้วก็ส่งไปอินเดียรับซื้อเยอะเสร็จแล้วเขาซื้อไปกินซื้อเป็นสองอย่างเลยย้อมสีกับไปกินแต่ส่วนมากกินเขาก็ไปบดแล้วก็ไปผสมกับอะไรเอาปูขาปูอะไรก็เป็นพม่าก็กินแก่นะแต่คนไทยไม่กินแก่เพราะว่าเคี่ยวกัน
เซติคอนมันมีสองเจ้าที่ทำคนละ
เกษตรเหมือนกัน
เกษตรแอร์แสบเหมือนกันนะมีสองที่ในการสองท่านเคยเห็นอันหนึ่งไอ้นี่โมเดลไอ้เนี้ยแต่อีโมเดลนึงอ่ะมันจะใช้เหมือนเป็นคอมพิวเตอร์สายพันธุ์อ่ะเปลี่ยนใช้คอนเซ็ปต์เหมือนกันแต่ว่าจะไม่ใช้ยางโดนนั่นเองแต่ไม่รู้กันว่ากินเดียวหรือเปล่าไม่รู้ยางอะไรก็ไม่รู้เลยคอนเซ็ปต์ต้องมีคอนเซ็ปต์
แต่สีข้าวอย่างนี้กะลาไม่แตกสีอย่างนี้น่าจะกะลามันแข็งมากแล้วไม่แตกไม่รู้นะผมไม่เคยเห็น
อันนี้แยกนะอันนี้แยก
อันนี้เอาใยออกมา
ไม่อันนี้หัวใจเนี่ยผมว่ามีรูปมีเปลือกแล้วก็มีเส้นใยสั้นกับเส้นใยแบบโปรยกับเส้นใยหยาบรวมกันแยกมา3ส่วนเลยนะครับอาจารย์เนี้ยเปลือกไก่เนี้ยไม่ได้รวมกันไม่แยกออกเลยใช่ไงบอกแล้วอาจารย์ต้องทำเลย
แล้วไม่ออกแล้วอ่ะ
ไม่ออกเอามา3ส่วนนะ
แล้วกะลาอยู่ตรงไหน
ก็ส่วนที่เปลือกนะครับเปลือกก็
กะลามันอยู่ตรงไหนใช่
ไอ้ตัวกะลาใช่ไหมกะลาที่มันแยกออกจากเส้นใยด้วย
แสดงว่าเส้นใย
โอ้โหรู้ว่า
ไม่
ดีมาก
มันอาจจะมีก่อนมาปลูกเส้นใยก่อนปลูกเส้นใยเสร็จแล้วถึงจะไปเขาเปลือก
ใช่แล้วจะเป็นอย่างนั้นจะเป็นอย่างนั้น
แล้วก็เสร็จแล้วก็
แล้วก็ไม่ออกแล้วก็แยกออกสุดท้ายเอาเส้นใยออกก่อน
ถูกต้องถ้าสีเนี่ยขึ้นใหญ่
อันที่คอนเซ็ปต์ที่ผมถามเขานะ
แต่หยาบกับละเอียดมันก็ยังคง
ไม่มีคนอยู่
ใช่นั่นคือคนอยู่แล้ว